A very good morning. Today we are discussed about Hall effect, that is in semiconducting materials. The last topic, Hall effect. First, what is a Hall effect? In this topic, we have to cover some of the subtopics. One is definition. Second one, determination of N type. Third one, determination of P type. Fourth one, determination of Hall coefficient. And fifth one, experimental verification. And last one, application of Hall effects. Right. First one is definition. What is a Hall effect? Hall effect is nothing but when a semiconducting materials current carrying x direction perpendicular to the magnetic field and the potential difference is appear both x and z directions, which means this is just like that a semiconducting materials, the current carrying x direction, the potential difference is that is perpendicular to both current and magnetic field, which is called Hall effect. So what is the application of this Hall effect is, you have to find whether the materials, that is semiconducting materials, N type or P type, which is based on the charge carriers, which is based on the charge carriers. We have to find whether the material N type or P type is the definition of Hall effect. So once again I tell you, this is a semiconducting materials, the current carrying x directions, the magnetic field through z directions, the inside the semiconducting materials potential difference is appear perpendicular to both current and magnetic field, which means y directions, This effect is called as Hall effect. Right. Second one, we have to find determination of N type semiconductors. Determination of N type semiconductor. This is semiconductor. The current is along x directions, Ix. The magnetic field through z directions, that is B. And the potential difference up here is z directions, sorry, y direction. The potential difference is up here along y direction. Already know that the Hall effect, the current carrying x directions, the magnetic field along z directions, the potential difference is up here perpendicular to both x and z direction, which means y directions. Now the electron move from right to left. The more number of electrons accumulation bottom of the slab when compared to top slab, so a small amount of holes accumulated top of the slabs, but the more number of electrons accumulated in bottom of the slab, that is slab 1, slab 2, and due to the potential difference, the upward directions, upward transition energy E, E, H, and the downward energy due to magnetic field B, E, V, B, E, V. Now the downward energy due to magnetic field is equal to B, E, V. This is equation number 1. Here more number of electrons in bottom of the slab, a small amount of holes top of the slab. Due to the positive and negative charges, the potential difference occurs, and the energy is upward transition EEH, upward transition EEH. The upward transition is due to potential difference, which is equal to EEH. This is equation number 2. Now at equilibrium conditions, the downward transition is equal to upward transitions. Downward transition is equal to upward transitions. Now equating equation 1 and 2, that is upward transition is equal to downward transitions. Upward transition, you know that E H is equal to downward transition B E V. Then EH, the Hall field EH is equal to B V. This is equation number 3. The Hall field EH is equal to B V. Already you know that the current density in terms of velocities, current density in terms of velocity, the current density in terms of velocity that is Jx is equal to minus NeV. The minus indicating the electron move towards negative y directions, negative y direction, that is Jx is equal to minus NeV. This is equation number 4. From this equation you can write the value of V, that is velocity V is equal to minus Jx by Ne. It's equation number 5. The velocity V is equal to minus Jx by Ne. Now substituting equation 5 in 3, substituting equation 5 in 3, you will get the value of Hall field, that is EH is equal to B V is equal to Jx by Ne, the negative side. EH is equal to minus B Jx Ne. This is equation number 6. From this equation you can write the value of Hall coefficient. This EH is equal to RH Jx B by EH is equal to RH Jx B. This is equation number 7. Now the value of RH, Hall coefficient, RH is equal to minus 1 by Ne. This is equation number 8. From equation 7 you can write Hall coefficient. This RH is equal to EH divided by Jx B. RH is equal to EH divided by Jx into B. This is equation number 9. This is the determination of N-type semiconductors. The next one is determination of P-type semiconductors. The P-type semiconductor, now Next one is the determination of p-type semiconductors. The current carrying x direction, the magnetic field along z direction, the potential difference is up here perpendicular to both x and z directions, which means y directions. This is Hall voltage. This is semiconducting material, semiconductor. Now, when I apply the current, the electron move from left to right. In those case, n-type semiconductor, the electron move from right to left towards downward direction. Here, in p-type semiconductor, the electron move from left to right towards downward directions. And here, the majority of charge carriers is holes which are accumulated in bottom of the slab. A small amount of charge carriers which are accumulated top of the slabs, which is electrons. Now the downward force, already you know that B E V, which is due to the magnetic field, and upward force, which is due to the potential difference, that is E EH, E and EH. Now the current in x directions, the more number of holes accumulated bottom of the slabs, more number of holes accumulated bottom of the slabs when compared to the electrons. Here more number of holes accumulated in bottom of the slab due to the positive negative charges, the potential difference is appear. The potential difference is appear. Already you know that upward force due to potential difference, upward force due to potential difference, which is E EH. This is equation number 1. Then downward force acting on a body, which is downward directions, the more number of holes accumulated, downward force due to magnetic field, which is B E V. This is equation number 2. Already you know that at equilibrium conditions, upward force is equal to downward force. That is equal to equation 1 and 2. equating equation 1 and 2, that is E here equating equation 1 and 2, that is already know that equation 1 is upward force due to potential difference, equation 2 is downward force due to magnetic field. Now equating equation 1 and 2, that is EH is equal to BEV, it's equation number 3. Now E, so you can write EH is equal to BV, EH is equal to BV, this is equation number 4. Already you know that the current density in terms of velocity, the current density Jx is equal to NEV. In those case, that is n type semiconductor, we are indicating negative sign minus NEV. Why we are indicating negative sign is the potential difference is appeared towards negative y directions, that's why we are indicating minus NEV. But here the current density Jx is equal to NEV, so we can represent holes, so NHEV, NHEV. For our convenience, we can represent the holes, which means p type semiconductors. This is equation number 5. Now substituting equation 5, from equation 5 you can write the velocity v is equal to Jx by NHEV, is equation number 6. Now substitute equation 6 in 4, substituting equation 6 in 4, substitute equation 6 in 4, here the Hall field, substituting equation 6 in 4, the Hall field EH is equal to the value of B, instead of the V values, Jx by from equation 5 V is equal to Jx by Ne. The substitute equation 6 in 4, from equation 5 V is equal to Jx Nhe. Now substitute equation 6 in 4, that is Eh is equal to B Jx by Nhe. From this equation 7 you can write the Hall coefficient RH is equal to 1 by Nhe. This is equation number 8. So you can write the equation 7, Eh is equal to B RH Jx. This is equation number 9. This is Hall field. From this equation 9 you can write Hall coefficient RH is equal to EH divided by Jx B. This is equation number 10. The equation 10 represents Hall coefficient for p-type semiconductor. Next, determination of Hall coefficient. Determination of Hall coefficient. Then we have to find Hall coefficient in terms of Hall voltage. By using Hall voltage formula, we have to find Hall coefficients. Already you know that if you are taking the materials with the thickness of T, so you have to find the Hall voltage VH is equal to EH into thickness of the sample. The Hall voltage VH is equal to EH into T. This is equation number 1. Already know that the value of EH from the above equation, EH is equal to RH JX B. This equation already you have to derive the above equation. EH is equal to RH JX B. Then substitute in these values, VH is equal to RH JX B into T. This is equation number 3. Here the Hall voltage VH is equal to RH JX B into T. Then you know the value of the current density Jx. The current density Jx is equal to, that is current density J. Now here the current is passing through the x directions, so Jx is equal to Ix by A, which means area A. Already you know that the semiconducting material thickness T, then breadth B, so the area of cross section breadth into thickness. That is B, small b into T. Now you can write the current density Jx is equal to Ix by small b small t. This is equation number 4. Now we have to substitute in equation 4 in 3. Substituting equation 4 in 3. Here instead of value of Jx we can substitute. Then the Hall voltage VH is equal to RH Jx instead of Ix, then B T divided by small b and T. This is Hall voltage. VH is equal to RH Ix B T divided by small b and T. This is area of the cross sections. Now T cancel each others. Then you have to write the Hall voltage VH is equal to the RH Ix B divided by small b. This is equation number 5. This is Hall voltage in terms of Hall coefficient. Now we have to find Hall coefficient in terms of Hall voltage. From this equation you can write the Hall coefficient, that is Hall coefficient RH is equal to VH into small b divided by Ix into capital B. This is equation number 6. The equation 6 represent Hall coefficient in terms of Hall voltage. The next one is determination of Hall coefficient by experimental method. Determination of Hall coefficient in terms of experimental method. Hall effect by experimental verifications. Hall effect by experimental verifications. Already know that. What is Hall effect? When the current carrying x directions, magnetic field through z directions, the potential difference is appear perpendicular to both x and z directions, which means y directions. Here the x direction is a current apply x direction Ix, the magnetic field This is a Hall effect experimental verification. Now we are taking a semiconducting sample which is in the form of a rectangular shape. The breadth is B and thickness is T. The current is through x directions which is connected to a battery and a milliammeter to measure the voltage, current, then key, then reverse charge. Then this material subjected to an external magnetic field, that is north and south pole. The induced magnetic field which create Hall effect, that is the Hall coefficient values RH is equal to VH B divided by Ix into B. This is Hall coefficient formula. Then what are the application of Hall effect? What are the application of Hall effect? Already I told you, the first one is to determine whether the material is N type or P type, which is based on Hall coefficient sign. First one is determination of the type of materials. Which means on the based on sign, that is RH is equal to 1 by minus 1 by Ne, means the negative sign indicate the material is in the form of N type semiconductors. Then RH is equal to plus 1 by Pe, means that is positive sign which indicates P type semiconductor. On the based on sign, we have to classify the materials whether it is N type or P type. The second one is to determine mobilities, mobility. Determination of mobility. Already know that the electrical conductivity sigma is equal to sigma E is equal to N E mu E. Then from this equation you can write mu E is equal to sigma E divided by N E. Already you know that mu E is equal to sigma E into RH. Here the value of RH is equal to 1 by Ne. So you can find the mobility of the electrons. Mu E is equal to sigma E RH. Next one is determination of carrier concentration. Determination of carrier concentration. Already you know that the Hall coefficient RH is equal to 1 by Ne. From this equation you can find the carrier concentration. Carrier concentration N is equal to the carrier concentration N is equal to 1 by RH E. By using this equation you can find the carrier concentration of electron and carrier concentration of holes. Then some of the Hall devices, already you know that some of the Hall devices, there are 3 devices in your syllabus. One is Gauss meter, second one is electronic multiplier, then third one is electronic wattmeter. So these are all the some of the Hall devices: Gauss meter, electronic multiplier, third one is electronic wattmeter.